Welcome back to the deep dive. Today we are tackling something that strikes, it strikes fear into the hearts of sysadmins everywhere.
Oh, yeah.
We're talking about the blinking cursor, the ticking clock. We are diving into the CKA.
The Certified Kubernetes Administrator exam. It's infamous for a reason.
It really is. And look, we've had a ton of requests from you to cover this, but we didn't want to just sit here and give you a list of commands to memorize, because the CKA isn't really a multiple-choice memory test, is it?
No, not at all. And that's exactly where people fail. Most IT certifications, they ask you what flag does X do?
Right.
And you just pick A, B, C, or D. But the CKA, it gives you a legitimately broken cluster and just says, fix it.
Yeah, it's performance-based.
Exactly. If you don't actually understand the architecture, you just can't fake it. You can't just guess C and hope for the best.
Right. You can't just guess your way through a broken control plane. So we've pulled together a specific set of high-yield practice questions today, and we're going to use these not just to test you, but to completely deconstruct the logic of Kubernetes.
Yeah, we want to get you into the headspace of the exam creators.
Exactly. We want to figure out the why behind the what.
Which is really the only way to pass. You have to understand the system as a whole, not just memorize the syntax.
But before we get into the weeds, and we are definitely going to get into the weeds today, let's look at the map. We have the official exam domain breakdown right here. If I'm a learner, right, and I only have limited study time, where is the highest ROI? Where should I be panicking the most?
Well, if you look at the source data, it is heavily weighted towards keeping things running. The heavyweight champion, without a doubt, is troubleshooting.
Yeah.
That section alone is 30% of your score.
Nearly a third of the exam is just fixing things that are broken.
Which reflects reality, doesn't it?
I mean, yeah.
Administrators spend their lives debugging. After that, you have cluster architecture, installation, and configuration coming in at 25%.
Okay, so just between troubleshooting and knowing how the thing is actually built,
yeah,
that's 55% of the exam right there.
Precisely. The majority.
So if you can't install it and you can't fix it when it breaks,
you're done. You're not passing. Then you have services and networking at 20%, workloads and scheduling at 15%, and storage coming in at 10%.
Poor storage. It's always the underdog.
It is, but don't sleep on it. I mean, 10% is easily the difference between passing and failing. But the big takeaway for you here is, if you focus only on deploying apps, but you have no idea how to troubleshoot why they crashed, you aren't getting certified.
Loud and clear. So let's start with that 25% chunk, the architecture. I always like to think of this as the brain of the cluster.
That's a really good analogy. It controls literally everything else.
Let's look at question 1 from our stack. It deals with keeping the ship on course. The scenario is this. You have a cluster running. You've told it what you want, but something fails. The question asks, which component is responsible for maintaining the desired state of the cluster by performing routine tasks, such as replacing failed pods?
This is fundamental. This is basically the heartbeat of Kubernetes.
So the options are A, controller manager, B, scheduler, C, API server, or D, cloud provider interface. Now, I feel like a rookie might just jump straight to the scheduler here.
Oh, a lot of people do. It makes intuitive sense. You think, well, the scheduler puts things places, so it must be the thing that fixes them.
Right.
But the scheduler is really just a seating host at a restaurant.
Oh, I like that.
Yeah, its only job is to look at a pending pod and say, you sit on node 3. Once the pod is seated, the scheduler completely stops caring. It goes right back to the podium to wait for the next guest.
So it doesn't care if the pod, dies 5 minutes later while eating its appetizer.
Not at all. That is not its department. The correct answer here is A, the controller manager.
Walk us through that. Why the manager?
Think of the controller manager not as a single solid thing, but as a collection of loops that just never stop running.
Okay.
It has the node controller, the replica set controller, things like that. It is constantly looking at the current state, like what is actually happening right now, and comparing it to the desired state.
Which is what you wrote in your YAML file.
Exactly.
So if I said, I want 3 web servers and one just crashes.
The controller manager sees, okay, desired is 3, current is 2. It notices the drift. It triggers the action to create a new pod to bring the count back to 3. It's the engine of reconciliation. Without it, Kubernetes is literally just a static database.
That word reconciliation is the key, isn't it? It's that self-healing capability.
Exactly. It's what makes Kubernetes declarative. You declare what you want, and the controller manager fights to make it true.
Okay, staying on architecture, let's look at question 7. This one is about the sequence of operations. And this trips people up because it feels like a chicken and egg problem.
Right, this is about upgrades.
Yeah. The scenario says, according to standard maintenance practices, which part of the infrastructure should generally be upgraded first during a cluster version update?
This is critical, because if you do it wrong, you can completely lose control of your cluster.
So the options we have are A, worker nodes, B, container runtime, C, control plane, or D, external storage.
The answer is C, the control plane.
Now, play devil's advocate for me for a second. Why not upgrade the workers first? Just get the heavy lifting out of the way.
Imagine you were in an army. If you give the frontline soldiers new orders and new maps, like a totally new version of reality that the general hasn't even seen yet, chaos ensues.
The soldiers are suddenly smarter than the general. That's dangerous.
Exactly. In Kubernetes, the control plane, the API server, that controller manager we just talked about, needs to understand the newest version of the protocol before the nodes try to speak it. I see.
You always upgrade the master components first to stabilize the management layer. Then you upgrade the workers one by one.
So the brain gets the upgrade before the body.
Always. If you do it backward, you risk the control plane simply not understanding the status reports coming back from the updated nodes. You might have version skew issues where the API server just rejects the kubelets messages.
That makes total sense.
Oh.
Okay, let's actually move from the brain to the body, the workloads and scheduling part. This is about where things run.
Right, the 15% bucket.
We have question 2 here, and this introduces a concept that I always visualize as a VIP rope or maybe like a biohazard sign. The question asks, what mechanism is used to repel a set of pods from being scheduled on a specific node unless those pods have a matching exception?
Notice the word repel there. That is the massive hint.
Right. Options are A, node affinity, B, taints, C, resource quotas, D, priority classes.
The answer is B, taints.
Taints. It just sounds negative. It is negative by default. A taint is applied to a node. It essentially says, do not schedule anything here. It's like putting a wet paint sign on a park bench. Unless the pod has a matching toleration, it's like having a special pass that says, hey, I don't mind wet paint.
Give us a real-world use case for this. Why would I ever want to repel pods? Why wouldn't I want my cluster fully utilized?
Imagine you have a node that has a super expensive GPU attached to it.
Okay.
You're paying, say, $10 an hour just for that node. You absolutely do not want a random low-priority Nginx web server landing there and taking up space.
Right. That's a massive waste of money. You want that GPU reserved for your machine learning models.
Exactly. So you taint the GPU node. The scheduler sees the taint and just refuses to put normal pods there. Only your specific AI training pods, which you've deliberately configured with the matching toleration, are allowed to land.
So taints and tolerations work together to dedicate resources.
Exactly. But remember, taints repel. If you want to attract pods to a node like saying, this pod must run on the fast SSDs, you'd use node affinity.
Oh, that's a great distinction.
The exam loves to test if you know the difference between repelling and attracting.
Repel versus attract. Good to know. Now, what if we don't care about where, but we actually care about coverage? This brings us to question 6.
The everywhere question.
The scenario reads, which workload resource is best suited for ensuring that a specific system-level pod, such as a log collector, runs on every single node in the cluster?
And the options?
A, stateful set, B, daemon set, C, replica set, D, deployment.
It's B, daemon set.
But why isn't this just a deployment? I mean, if I have 10 nodes, why don't I just create a deployment with 10 replicas?
You could do that, but what happens when you add the 11th node?
I'd have to go in and manually update the deployment scale to 11.
Exactly. And you don't want to be doing manual math at 3 in the morning. A daemon set doesn't care about a count. It cares about the nodes. If you add a brand new node to the cluster, the daemon set controller automatically sees it and spins up a pod on it immediately.
And the use case mentioned, log collectors, that's the classic example, right?
That, or a monitoring agent like Prometheus Node Exporter, or even the CNI networking plugin itself.
Right.
Anything that needs to run on the actual metal of every single server needs to be a daemon set. It guarantees 100% coverage without you lifting a finger.
Got it. Okay, one last question on the body of the cluster before we move on. Question 5. This is about the health check. What is the standard status of a node when it is healthy, communicating with the control plane, and ready to accept new workloads?
See, this sounds deceptively simple.
Options are A, ready, B, active, C, connected, D, running.
It's A, ready.
I bet so many people pick running.
They do, because pods have a status of running, but nodes are infrastructure. Their status is ready.
And who actually decides that? Who flips the switch?
The kubelet. The agent running on the node itself. It sends a heartbeat to the API server every few seconds. If the heartbeat stops or if the node runs out of disk space or something, that status immediately flips to not ready.
And going back to our friend the scheduler.
The scheduler looks at that exact status. If a node isn't ready, the scheduler crosses it off the list and won't send any new work there. It all connects.
It's a beautiful system when it actually works.
When it works, yes.
Let's talk about when we need to talk to the outside world. The nervous system, services, and networking.
This is 20% of the exam, and usually the part people struggle with the most because it involves IP tables and routing.
Let's simplify it then. Question 4 asks, which service type is specifically designed to expose an application to external traffic by utilizing a cloud provider's external load balancer?
Options.
A, node port. B, cluster IP. C, external name. D, load balancer.
The answer's right in the name. D, load balancer.
Kubernetes developers are nothing if not literal.
It's true. But the magic here is really the automation. If you create a service of type load balancer, Kubernetes actually reaches out to AWS or Azure or Google Cloud. It says, hey, I need a static IP and a load balancer, and the cloud provider provisions a real piece of infrastructure.
That's great for one app. But here's the deep dive insight I want to get at. If I have 50 microservices and I use type load balancer for all of them.
You are going to go bankrupt.
Right. Because the cloud providers charge you for every single load balancer you spin up.
Exactly. Plus, managing 50 different external IP addresses is just a nightmare for DNS.
Which sets us up perfectly for question 10. This is the solution to that bankruptcy problem. The scenario is, which resource functions as an entry point for external traffic and uses a collection of rules to route requests to multiple internal services based on the URL path?
And the options are?
A, network policy.
Yeah.
B, ingress controller. C, gateway interface. D, proxy server.
It is B, the ingress controller.
So how is ingress fundamentally different from the load balancer we just talked about?
Think of the load balancer as a phone number that goes directly to one specific person's desk. Think of ingress as the main switchboard for the whole company.
Oh, I really like that analogy.
Yeah, you have one load balancer, one phone number that connects to the ingress. The ingress answers the call, checks the rules you wrote, and says, oh, you want /billing? I'll switch you to the billing service. You want /store? I'll switch you to the store service.
So it operates at a higher layer.
Exactly. It's layer 7, HTTP, and HTTPS routing. The load balancer is usually just layer 4, which is simple TCP. The ingress allows you to host dozens of services behind a single external IP address. It's cleaner and, frankly, much cheaper.
Efficiency wins again. Okay, let's touch on storage briefly. We mentioned it's only 10%, but this specific question comes up a lot. Question 3.
The access modes.
Yeah. Which storage access mode allows a volume to be mounted as read-only by many different nodes simultaneously? Options are A, read-write once. B, read-write many. C, read-only many. D, single user access.
The answer is C, read-only many. In the YAML, you'll actually see it written out as ROX, ROX.
Why would I want read-only, though? Don't applications need to write data?
Not all of them. Think about an AI cluster. You have a massive data set, terabytes of images. You have 50 worker nodes that all need to process those images at the same time. They all need to see the data, but you absolutely do not want them changing the source state.
Right. You don't want one rogue node accidentally deleting the training set.
Exactly. Read-only many allows massive parallelism for consumption without the risk of corruption. It's a safety feature as much as it is a storage feature.
Speaking of safety, let's talk about permissions. Question 8 covers RBAC, role-based access control.
Such a critical topic for security.
The question asks, in the Kubernetes authorization system, which object is used to define a specific set of permissions that apply only within a single namespace? Notice the emphasis on single namespace there.
Options.
A, cluster role. B, security context. C, service account. D, role.
It is D, role.
And this is where the blast radius concept comes in, right?
Yeah.
What is the actual difference between a role and a cluster role?
Scope. A cluster role is global. If I give you a cluster role to delete pods, you can delete pods in production, in staging, in the CEO's personal demo project, literally everywhere.
Dangerous.
Very. A role is locked to a namespace. If I give you a role for the dev namespace, you can be God King inside dev, but you cannot even touch production.
So for the exam, if you're reading a question and you see namespace specific, you should immediately think role. If you see an entire cluster, think cluster role.
Spot on. And remember, you need a role binding to actually attach that permission to a user. The role is just the definition. The binding is the key that turns it on.
Great tip. All right, we have reached the end of our stack, and we're circling right back to where we started. The heavyweight champion. Troubleshooting.
The final boss, question 9.
This is the tool you need when everything goes wrong. Where can an administrator find a record of state changes, errors, and significant lifecycle occurrences for objects within a namespace?
Also known as the flight recorder.
Options are A, events,
Uh-huh.
B, snapshots, C, config maps, D, endpoints.
The answer is A, events.
I feel like beginners always ignore kubectl get events. They just go straight to the pod logs.
They do, and it is a fatal mistake on the exam. If a pod is crashing after it starts, sure, check the logs. But what if the pod never starts?
Oh, then the logs would just be empty.
Exactly. If the image name is spelled wrong, or the scheduler can't find a node that fits, the application itself never runs, so it never writes a log. The only place that error exists is in the Kubernetes events.
It tells you what the platform is doing to your workload rather than what the workload is doing.
Image pullback off, failed scheduling, unhealthy. These are all events, but here is the major pro tip for you on this. Events are ephemeral.
Wait, they disappear?
By default, they only last for about an hour in the cluster.
Right.
If you come in on Monday morning to debug a crash that happened on Friday night, the events will be gone.
Wow. So you need to catch them in the act or have some external system to export them?
Exactly. Don't rely on them strictly for historical forensics unless you are shipping them to a log aggregator somewhere. But for live troubleshooting on the CKA exam, it is the very first command you should type.
Kubectl get events. Tattoo it on your arm.
Or maybe just write it on the whiteboard they provide you during the exam.
Thanks for joining us on this deep dive. Keep those notes ready, and we will catch you on the next deep dive.